Okay, so here is what you really kind of need to know about continuity. Basically, when we talk about continuity of a function is continuous if there are no breaks, no holes, no gaps, if it is a smooth function. Now, I have to put a little caveat on that because you can get into instances where you have a function that does not appear to be continuous, but they call it continuous over its domain. But that is a little bit more than you need to know. So let's just do the basics right now. For a function to be continuous, there are three things that have to happen. And the first thing is that there is a value everywhere. So we say that no matter what number I put in for the function, I'm going to get an output value. So there's a value everywhere. F of a exists. So there is a value everywhere. The next thing that has to happen is the limit as x approaches any value for that function also has to exist. So that means, again, not only is there a value everywhere, but there is a limit everywhere. Okay, so the last part is that not only is it enough to have a value everywhere and enough to have a limit everywhere, we have to also make sure that every value equals its limit at every location. And this stuff gets a little bit wordy. So I always think it's way easier to see it in a picture where you can just sort of look at what it is I'm talking about. So I'm going to give you a few drawings and then we'll talk about each of those drawings. So like for example, this is a continuous function. And you notice that there are no breaks or no holes. I even put the arrows in on the end. There's nothing that goes on. It's got some curves. It even looks like it's got a little point right here. Doesn't matter, flattens out. Doesn't matter what it does. There are no breaks. There are no holes. There are no nothing. We call this a continuous function. Okay, so the problem happens when any one of these things here fails. So let's start with the first one. I'm going to show you a function where it doesn't have a value everywhere. And so if I just draw a quick little graph here, everything's good, and then all of a sudden I have a little hole. Okay, so in this one, I have no value at wherever this location is, if I call it any number. The first stop here fails. We call this, I've heard it referred to as a hole. I've heard it referred to as removable. And I've also heard it referred to as a point discontinuity. Now, I don't love the hole definition or it being called a hole because I'm going to show you there are situations where it looks like there's a hole, but there really isn't a hole. And so removable and point discontinuity are a better way to call that. So this is removable or point discontinuity. And that's, again, where the first thing fails. Okay, so now let's look at the next one. We're going to draw a picture where, or I'm going to draw a picture where it doesn't have a limit everywhere. That there's a spot where, remember the definition of a limit is that on both sides of a particular point the graph comes together. And so here the limit exists at A because on both sides of this hole the graph comes together. It's just that there's no value there. So what does it look like to not have a limit everywhere? Well, that would be a function where, I don't know, maybe I stop here and then I drop down here and have another. So there's an example of a spot where the limit does not exist. This is called a jump discontinuity. Okay, so where the first one is continuous, I have a limit, or I have a value everywhere, a limit everywhere, and they always are the same. It always connects at each side of the point. Here's where I don't have a point, I'm missing a point. Sometimes I could even put a point above that and it's still, oh, no, nope, I can't do that, because then then it has a point everywhere. So that goes into our last step. I'll get into that picture. Okay, so this is removable or point discontinuity. Here's a jump discontinuity. Here's another situation where I don't have a limit everywhere in a picture. So let's say I have an asymptote in here, and so here the graph goes. Everything's fine except for there's no value and no limit where you have an asymptote. That's called an infinite discontinuity. Okay, so we have discontinuity. Sorry for my inefficiency here. But so we have removable, we have jump, we have infinite. Now we also have another situation. That's the one where I was kind of starting in here and I was getting ahead of the game, so I want to talk about that last situation. There are instances where, I'm going to draw one last picture, where I can have a limit everywhere and a value everywhere, but the third thing fails, and that means they don't exist. And so that's when I have this situation where maybe I have another function where it's got this hole, but then we fill it in with a point. So I have a value, 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 I have a value everywhere. So I have a value everywhere. So f of a always exists. I have a limit everywhere. In every spot that I look, I can draw little arrows pointing at each other, and there is always, even at where that point is, I still have a limit there because it still goes to that hole on both sides. Everywhere there's a limit. Here's the problem. Right at this location, whatever this value is, again, I could call this A, at this location, I don't have the point and the limit in the same spot. Okay, so that's where a situation where the third step fails. Now, I talked about a lot of stuff, and I don't want you to overthink it. I just want you to kind of look at the pictures and see if you can decide, well, is this a continuous function or not? And if it's not continuous, we can tell where it fails, and we can tell why it fails. And when I'm talking about why it's not continuous, I'm talking about, is it removable or point? Is it jump? Is it infinite? What's the issue? Okay? So this, back to this one here again, this is another removable or point situation. It's just different from this first removable or point situation, because in this one I didn't have a value everywhere, but in this one I do have a value. Okay, so when I look at this first graph, notice no holes, no breaks, no jumps, no nothing. What do I say about this graph? I say it's continuous. Done. That's it. Okay. What about this function? Well, I notice this asymptote here. So this is not continuous. Not continuous. Where does it fail to be continuous? It fails at x equals, right there, looks like x equals 1. That's where it fails. It's not continuous. It's not continuous at x equals 1. And why is it not continuous at x equals 1? Because it's got an infinite discontinuity. That means it's got an asymptote there. You could even just say there's an asymptote. It's just easier to spell infinite. So asymptote. There's my reasoning. It's not continuous. It's not continuous at x equal to 1 because there is an asymptote there, and we call that an infinite discontinuity. Okay, so when we move on to 3, again, I apologize for the blurriness of my camera. I don't have great material to work with here, but hopefully you get the point. There's a little hole in this one right there. I darkened it a little bit, but there's a hole in this graph, okay? So when I talk about whether or not this is continuous, I say that this is not continuous. Again, it fails at x equal to 1. Why does it fail? Because there is a hole in this graph, or better than that, it's got a removable discontinuity. A removable discontinuity, meaning there is this spot where there is a point that's moved out. And so lastly, number 4, I suppose not lastly, there are a couple more that I'll let you try on your own. And then you can just kind of question if you have questions on them, just let me know. This graph, my printer's running out of ink, so this graph kind of looks like this. I'm just going to darken it up a little bit. But again, it's solid there. This is another situation where just looking at the graph, I can tell there's a problem. There is this spot where it's broken. And because it's broken, it's not continuous. And it's not continuous, it fails at x equal to -2. That's where it fails. Everything else looks good. It's not continuous at x equals -2 because that's the spot where the break is. And what kind of discontinuity do we have? We have a jump discontinuity. The jump ones to me I think are pretty easy to recognize because it jumps from one part of the graph. You have to physically, if you could walk on the graph, you'd have to physically jump from one spot to the next to get to the rest of the graph. So that makes it a jump discontinuity. Okay, so that's the basics of continuous functions. I put 4 more. I shared the worksheet with you, so I put 4 more on the worksheet that you can try, and then I'll also send the answer key so that you can double check and see how you did. But really, if you can do this, tell me if it's continuous or not continuous, tell me where it fails and why it fails, you're in really good shape, okay? But we'll get down to the bottom because sometimes we don't have a graph to look at. And so there are 2 scenarios that really are very common for us. And the 2 scenarios are if I have a rational function, there is a potential for a location where it's undefined, creating an asymptote. If I have a piecewise function, there is a potential for the piecewise function not coming together. So my 2 ways of checking those 2 things are, first of all, is it a rational function? If it's a rational function and it has a denominator, can the denominator equal 0? That's what I have to ask myself. And sometimes I'm going to have to factor, and I might have a more than one spot where the denominator can equal 0. So in fact, I think what I'm going to do is I'll go through 10 and 12, and then I'll let you try 9 and 11. So for 10 and 12, I'm going to jump down to 12 now that I've sort of started with that. Can the denominator, this has a denominator, can the denominator equal 0? And denominator equals 0, can it? Is what I have to ask myself. And so what I'll do is I'll take that denominator, can x squared minus 2x minus 3 equal 0? Well, yeah, it can. I have to factor this to get it equal to 0. So when I factor it, I get x minus 3, x plus 1. Double check and make sure that's x squared plus 1x minus 3x. That gives me my minus 2x minus 3. So the denominator can equal 0 when x minus 3 equals 0 and when x plus 1 equals 0. And so it's at x equals 3 and at x equals -1. And so is this function continuous? No. It fails because it can have a denominator equal to 0, which creates an asymptote. So this is not continuous. Continuous, holy cow, I don't know what I'm doing there. At those 2 points, creating an infinite discontinuity. Okay? So if there's a denominator, there's an issue. Trig functions can have an issue too, like if you think about graphing tangent or graphing secant where we have asymptotes in the graph, those are going to cause a problem. So if I said to you, is the tangent function continuous? We'd say no, because there are asymptotes in it, so it has infinite discontinuities. If I had you write all the places where it wasn't continuous, it could take a while, and I'm not going to have you do that, so you just have to recognize, can a rational function be continuous? It can be if the denominator won't ever equal 0. All right, so what about a piecewise function? Well, in order for a piecewise function to be continuous, that means when I graph the function, the first part and the second part need to connect. And so here I have an issue at 0. That's where the function changes. And so I need to make sure that at 0, these two things come together. So all I want to do is plug in 0 as 0 over 2 minus 1, the same as the opposite of 0 squared plus 2 times 0. So 0 over 2 minus 1 is negative 1. The opposite of 0 squared plus 2 times 0 is 0. They are not equal, and therefore this is not continuous. Now, it is continuous everywhere else. This is the they issue. This is just a line, and this is just a parabola, and this is where they break and come together, and they actually don't meet here. This is where the left-hand side stops and the right-hand side begins, and they don't meet here, so they're not continuous, and they're not continuous at x equal to 0. And if I were to draw that, and I don't even have to, just because I know this one at 0 is negative 1 and this one at 0 is 0, we call that a jump. It's not connecting in the same place. Okay? So again, if I don't see a graph, the two main issues that we're going to see are asymptotes, which come from rational functions or trig functions, or piecewise functions where we have jumps or changes in the function. All right, so then the last thing that was kind of touched on in the Khan Academy videos that I think is important to talk about is how I can make a function continuous. And so I'm bringing back another scenario where I have these rational functions. And remember, in a rational function, when the denominator is 0, is where you have an asymptote. And so if I want to rewrite this function so that it's continuous for all real numbers, oh, I think I have an issue here, actually. And I know I do. So I am going to stop here, and I have the wrong types of problems that I want to do here. And actually, we'll get rid of those. Let's not look at those, and I'll show you what I really mean instead of me starting all over again or doing a different video. Okay, so what can happen here is we could have something like x squared minus 1 over x plus 1 as our function, the function that we're looking at. And so if I plugged in negative 1, I would end up with a location where it's 0 over 0, or a situation where it's undefined, where I have a problem down here where the denominator can equal 0 again. So x plus 1 equals 0 at x equal to negative 1. So if I want to, and I can't do this with every function, but some functions I'm able to do it with. If I want to rewrite this as a continuous function, what I want to do is I want to see if I can cross out that issue, x plus 1, x minus 1 over x plus 1. So then this gives me a hole in the graph. Well, in this function right here, this is my f of x, this is my function. The function does not exist at negative 1. So what I want to do to make it continuous is to get that piece out, and then I'll rewrite the function so that it is a continuous function. So I would say that my function is in piecewise form. This function that I said, x minus 1 over x plus 1, for everywhere except at negative 1, because that's where it doesn't exist. But then it is x minus 1, because that's where that hole was cut out, at x equal to negative 1. So all this does is helps me fill in the hole that I removed in that function. So I hope that, again, kind of makes sense. I'll do one more of those. And I don't want you to worry too much about that, because that's not a main topic. Really, like I said, the main topic is on this section is being able to recognize, is a function continuous? If it's not, where does it fail and why does it fail? That's the big stuff, okay? But just to do one more of those problems where we are going to make it continuous, I'm going to have my function f of x equals, let's do another one, not a bad one. Let's go with x squared minus x minus 12. We'll put that over x minus 4. And again, we will break this function down. Here's the issue, here's the problem. The problem where this is not going to be continuous, where I'm going to have a potential area of concern, is in that denominator at x minus 4. So I'm going to factor x minus 4, x plus 3, and take out that issue, x minus 4. And again, you can't always do this with every function. It doesn't work that way, but we can with some of them. And if we can rewrite it as a piecewise function, I'm going to make it work. Again, I'm going to make it whole. The issue was right here, what would make the denominator 0. So it's at x equals 4. So this is this function, x squared minus x minus 12 over x minus 4, everywhere except 4. And then it's what's left at 4. So all I'm doing is filling the hole to make this a continuous function. And I've really said more than I need to say about that. Again, the big takeaway here is the graph continuous? If not, where does it fail? And why does it fail? I hope that helped. As always, shoot me a text if you need a better explanation or want to see some more examples, and I'll see what I can do. Or sorry, an email. All right, have a good one. Bye.